Now ROC curve, called receiver operating characteristics curve, is a very important performance measure that we can plot in classification models. And this is first developed in a medical application, so it has a lot of medical. If you look at the literature, you will see that there are a lot of medical references to this. And here, ROC curve is plotted. On the x-axis, we have 1 minus specificity. Okay. On the y-axis, we have sensitivity. And we plot at various cutoff points. So, for example, here we have cutoff points going from 0 to 1. This is for the riding lawnmower example. So we have sensitivity, specificity, and then we have 1 minus specificity. I have a video where I discuss how to generate these numbers. Okay, so you refer to that video for actually setting it up. But here we are going to discuss only the concept. So we plot 1 minus specificity, okay, and then sensitivity on the x-axis, sensitivity on the y-axis. Then this is what the plot will look like. On the random case, okay, where you don't use any model and simply use random assignments, the graph, the ROC for that will be a line connecting 0, 0 to 1 and 1. Okay, so remember these are probabilities, so the valid range is 0 to 1 and 0 to 1. Okay, so this is called the ROC curve. All right, let's examine what this ROC curve actually is telling us. Okay, so here, if you look at the propensities based on which this ROC curve was generated, so we have cases going from 1 through 24, and you see that of all the owners, there are 2 of them with propensity was low. Okay, so that means these 2 owners would have been classified as non-owner, and there is one here who is a non-owner with a propensity of 0.78. So that means this person would have been classified as a owner. Okay, suppose if the probabilities had been slightly different. Okay, suppose instead of these 2 probabilities, these 2 were 0.6 and 0.7. And instead of 0.78, this probability had been 0.3. So that means you see that there is a cutoff point, there is a cutoff probability that clearly identifies all the owners as owners and all the non-owners as non-owners. That is, this classifier is perfect. There is a tuning value, that there is a cutoff probability. So here it will be like somewhere 0.6 would do it, I guess. Okay, so if it is 0.6, okay, even 0.5 will do it. So if you have 0.5 as the cutoff point, then all of these will be classified as owner, and they are actually owners, and all of these will be classified as non-owner. So if this is the propensity, and if you draw the ROC curve for this data, then this is what the ROC curve will look like. So the ROC curve will go straight up, okay, and then across. So which means, okay, so as the propensities go from, so let's look at with this revised propensities. Okay, what are the values of 1 minus specificity and sensitivity that gives us this shape? Okay, let's go to Excel for this. Okay, so here are the cutoff points. Okay, and with the revised propensity, you see that sensitivity is 1 all the way through here, right? When specificity, okay, remember, if a cutoff point is 0, then everything is going to be predicted as event, and some non-events will also get predicted as event. So your specificity is not going to be perfect, but it's going to be kind of some value. So it's going to change. 1 minus specificity will change. So at 0, everything will be classified as event. So specificity will be 0. So 1 minus specificity will be 1. So this point corresponds with here specificity 1, 1 minus specificity 1, sensitivity 1. So this point corresponds with 0 cutoff point. Okay, and here sensitivity is 0 and 1 minus specificity is 0. So that would correspond with a cutoff point of probability of 1, where everything is classified as non-event. So sensitivity will be 0 and specificity will be equal to 1, and 1 minus 1 will be 0. So everything in between. So what happens is, as the cutoff point increases, okay, your sensitivity will all be 1, but the specificity will increase, okay, and the 1 minus specificity will go down. So it will go down like that, like that, like that, until you reach the critical cutoff point, okay, like 0.5 in our case. So then you have now classified all the events correctly. So at that cutoff point, okay, so here, okay, 0.6. So what happens is, after that, your sensitivity starts to go down, but then at this point you have only non-events. When everything is now classified as non-events, all the non-events will get classified as non-events along with some events. So your 1 minus specificity will be 0. So there will be once, and 1 minus specificity will slowly go down, and then once it starts to be 0, then it will be 0 everywhere else, and the sensitivity will start go down. So there is a particular point at which your classes will be exactly classified, and that is what is represented here. Okay. What all this means is that if you have a model with ROC curve like this, that means there is some cutoff point at which the model will be perfect. At that cutoff point, all the events will be classified as events, all the non-events will be classified as non-event, and then the task will be to go and examine and see where that cutoff point is. And once you find that cutoff point, then you will have perfect classification. So the model capability, if the ROC curve is like this, then it is perfect, and this is where we compute what is called area under the curve. So we're going to specify area under the curve as 100%. So that will be all the area in the rectangle. Okay. Then this diagonal line is your naive classifier. So the diagonal line gives you an area under the curve of 50%. If this whole is 100%, this is 50%. So 50% is the baseline area under the curve. So if a model gives you 50% area under the curve, then that model is no better than random assignment, random classification. So the closer your ROC is to this perfect ROC curve, the better it is. Or in other words, if the area under the curve is closer to 100%, 100% being the ceiling. Okay. So that's what we are trying to achieve here. So area under the curve, okay, so which ranges from 1, the perfect discrimination between classes, to 0.5, no better than the naive rule. So the valid values for area under the curve is 50% to 100%, or 0.5 to 1.